sleeping.
You've already done this once. You already done this once.
Yeah, just a little different.
Well, I think
Okay, good afternoon, everybody. I'm gonna go ahead and get started in just a second. So, do you wanna do that? Yeah. Okay. One. Well, maybe both on actually. Yeah. My dad's recording it. Okay, so first of all, I'd like to thank everybody for being here. It means a lot to me. And today we'll be talking about a watershed scale spatial statistics approach for nutrient criteria development and classification scheme in Oregon lakes. And it's a mouthful, but we'll be talking about what nutrient criteria is and how to determine it, as well as why we want to classify these lakes for the purpose of criteria development. But before we answer those questions, you guys should know a little bit about Oregon lakes. So we have over 6,000 lakes and reservoirs in Oregon, and they are dispersed throughout the lake, but throughout the state, but concentrated in the Blue Mountains and Cascades primarily. In 2007, the National Lake Assessment estimated that just over 20% of the nation's lakes are nutrient impaired, and this makes it the second greatest cause of impairment after poor lakeshore condition. So, what does it mean to have nutrient impairment? So some of these things that can be impacted by high concentrations of nitrogen and phosphorus are designated uses of lakes, whether that's for public supply, like drinking water or irrigation, or recreation, swimming and kayaking, things like that. Fisheries, both recreational and commercial. And then those set aside for preserving the native ecology. Some of the ways that the uses can be impacted are algal blooms, fish kills, and reductions in water clarity. Some of our potential causes for concern in Oregon have to do with our land use. And here in the Willamette Valley especially, we have not only high urban concentrations, right? About 70% of the state, that's about 3 million people in this region, but we also have a lot of agriculture here. And so what does this land use mean for nutrient contribution to our lakes? Well, urban runoff can include things like stormwater, septic and sewer wastewater, home fertilizers, pet and yard waste that all can contribute nutrients, as well as some of our soaps and detergents. In terms of agriculture, this can look like animal manure or fertilizers, even soil erosion caused by our farming practices. In 2014, Oregon had over 35,000 farms across the state, covering 16.5 million acres. There's also 1.3 million cattle. That's about 1 cow for every 4 people in the state of Oregon. So to switch gears a little bit, I wanted to familiarize everybody with this concept of an Amernic ecoregion. In 1987, James Amernic came up with this ecoregion classification system for the United States, the coterminous United States, and it is 76 different regions across the country. So here in Oregon, we have 9, and these things are grouped together by vegetation, climate, geology, soils, the hydrology, the physiography, the species composition, and even some consideration of the human land uses of these areas. So as you can see, we have the Coast Range, the Klamath Mountains, the Willamette Valley, Cascades, the Eastern Cascades, the Northern Basin and Range, Blue Mountains, Columbia Plateau, and a little bit of the Snake River Plain in our state. When we're talking about management for nutrients, we refer to these nutrient ecoregions. And as you can see, they share some of the boundaries of those Amernic ecoregions because they're aggregates from that original 9 down into these 3 regions. So across the country, that's only 14 regions that have been aggregated from the original 76. These regions are suspected to have similar natural nutrient contributions. So here we have the Willamette Valley. We see a lot of the mountains have been aggregated to the western forested mountains and our desert, and grassland regions are the Xeric West. Some of the issues we have with there only being these three regions suggested for nutrient management is that these areas tend to be too broad to capture our local variability in natural nutrient concentrations. And so we have unimpaired lakes that are failing to meet the suggested criteria set for them. EPA is pushing to have some of the states to adopt their own standards, and currently there are only 16 states that actually have full criteria for all their water bodies, and there's 22 that have some kind of partial total phosphorus or total nitrogen criteria, or they have a chlorophyll A or second disc, something related to nutrient management. So here in Oregon, the Department of Environmental Quality has enforced this nutrient standard of 10 to 15 micrograms per liter of chlorophyll A, and that's a surrogate for our biological productivity in our lakes, like things like algal blooms. And we don't have a statewide nitrogen or phosphorus criteria. Now, locally, there are some city and county phosphorus criteria, and there's some lake-specific or site-specific criteria, but there's nothing on the state scale. And as of June 2014, the Department of Environmental Quality for Oregon released a qualitative plan for nutrient management, but didn't enforce anything in the way of establishing a numeric nutrient criteria. So what does this mean? Is that setting a hard number to meet as a standard for these different regions. And so right now there's a qualitative management implementation, but not something that we can really put a quantitative number to. Therefore, my research questions are, how can we determine the appropriate total nitrogen and total phosphorus criteria for our lakes? And how can we determine the best way to categorize these lakes that are similar to each other for management purposes? It's impractical and unreasonable to suspect that we can manage all lakes individually. And how are Oregon lakes currently performing when held to this proposed criteria? So the first research objective was to then determine the least or most minimally impacted lake for reference condition in each ecoregion. So a minimally impacted lake would be something that's pristine, or what in today's world, near pristine. And these lakes are typically available on protected lands versus something that is least impacted, which is kind of the best of less than ideal. So something that we might find here in the valley. And we do this by ecoregion because what might qualify as a reference site in the Willamette Valley would not in the Cascades. You can't hold two different areas to the same standard when those reference sites just aren't available. Our second objective is to group these similar reference sites by determining their important traits. Those look like lake and watershed characteristics that these areas have, and using a categorical and regression tree analysis and k-means cluster analysis. So we're going to compare these methods to see which way might be most effective for establishing nutrient criteria and classifying these lakes. Then we have the 75th percentile of our total phosphorus and total nitrogen of reference lakes for each category to be used for criteria. And we choose the 75th percentile so that we have a little bit of flexibility with management, and we can kind of weed out some of the potential lakes that snuck in as a reference condition that might not actually be. Lastly is the application of this proposed criteria. So we want to apply the criteria that developed from this thesis in order to apply it across a random set of lakes and see where we are today and how our lakes are currently performing. So using a set of random lakes from the 2007 and 2012 National Lake Assessments, they're randomly selected and weighted to represent the proportion of similar lakes in the state that might share those same conditions. In order to do all of this, we needed to start with the data set, right? So the EPA provided a 331 lake data set initially, and we're only interested in a subset of those lakes. So lakes that are greater than 1 hectare. We're not looking at any playa lakes, and no Columbia River or Snake River reservoirs. So within that 331, 309 lakes were share those characteristics, and all ecoregions were represented by those 309 lakes. Within those 309, we had multiple samples of nutrient condition for each of these, for most of these lakes, and some only had a single. The samples were all taken between 1967 and 2007. And they were all sampled from the Epilumnian. That's that top layer of the water column between May and October as a summer surface index value. So once this was condensed, we have these represented watersheds. So this is at 309 lakes. These are their watersheds and the distribution of them across the state. The dark blue represents like a primary basin, and the lighter blue represents some of the subbasins within those. As you can see, the Cascades have quite a few of those subbasins. In order to determine which lakes we were going to actually subset from that 309 to be a reference site, we considered some of these factors of anthropogenic nutrient addition. So these included things like that agriculture and urban development land use I was talking about in the introduction that we are linked to nutrient addition, as well as concentrated animal feed operations, road density, population density, and lakeshore use. These were all calculated using layers in GIS, except for the lakeshore use, which was used with the aerial photographs to qualitatively score lakeshore condition within 100 meters of the lake. And this was done across 7 categories, including residential and agricultural means, but also commerce, logging, mining, and recreation and roads that are within that 100 meters of the lake. So this is supposed to represent both the source and some of the transport of our nutrients. Once the reference sites were selected with that methodology, we then considered classification variables. Now these are supposed to be sources or circuits for transportation of our nutrients throughout the watershed. And therefore, our lakes that share similar classification variables are suspected to then have the same natural nutrient drivers. So things like elevation, the lake depth, the lake surface area, the slope of the watershed, the annual precipitation, the amount of deciduous forests that cover our watersheds, and the amount of wetlands in our watersheds, as well as a calculated residence time, the soil cation exchange capacity, and soil permeability, and then lastly our volume of runoff every year. Again, these were also calculated using GIS layers. Another classification variable considered, it still encompasses those physical traits that I mentioned before, right? Some of that physiography, geology and soils, climate, things like that. We have this ecoregion idea, and so currently, lakes are managed wherever the centroid of the lake is, and for some of our lakes that span multiple ecoregions, they're managed in a region where their watershed is hardly present. And so I wanted to see what percentage of the watershed is in each ecoregion in order to maybe establish a more effective management strategy. So I calculated what percent of every watershed was in each ecoregion, majority falling in where their lake was, but some of them spanning those boundaries. Once this was all calculated, it was time for the statistics. And so a series of statistical analyses were going to show us what some of these relationships were for classification. So I used ordinary least squares linear regression to show some of that concentration with our individual variables. Correlation matrices used to show us how correlated our variables are. Those that are highly correlated we don't want to include. They could just fog up the data and not actually correctly represent what we're trying to show. Some principal component analysis and multivariate adaptive regression splines were both used in order to determine some of those important variables, specifically for classification purposes. And then, of course, our CART, our regression tree analysis, which uses recursive partitioning in order to place a lake into categories using a tree. And k-means clustering as an alternative for comparison. We wanted to compare these methods. And so this uses clusters of similar lakes together by their shared properties. And every iteration is a little bit different. So some of the results of this methodology. Well, we have that 331 we started with, which was targeted down to 309 that we were considering for reference sites. And of those 309, only 98 lakes survived as being a reference site. And so all 98 had total phosphorus criteria, but of that 98, only 39 had total nitrogen concentrations associated with them. And so here you can see on the left, we have the phosphorus distribution of our sample, and on the right, we have our nitrogen distribution of our sample across the different ecoregions. And you can see that the Cascades and Blue Mountains are more represented. We have more lakes there than we do in some of these other regions, like the Valley and the Klamath Mountains. This is the distribution of our reference sites compared to our considered lakes. So the blue represent all the lakes that were considered, and the yellow represent the lakes that were actually chosen in this sample of 98. I wanted to show some examples of what a reference condition looks like for different ecoregions. So this is our best case scenario. Our Cascades and Blue Mountain ecoregions both have these properties, and we can see here that agricultural land and developed land, there's nothing of the sort in their watersheds. There's no roads and no animal feed operations. There's no permanent uses of lakeshore disturbance. I'm sure there's maybe some camping or something like that, but nothing that came up in the 100-meter lakeshore scores. And then this population density, where there's no roads and there's no development, there's probably no people, but due to the methodology used of averaging population over a census tract, we're going to get a little margin of potential error there. So in the Willamette Valley, this is going to be our worst, right? Highly concentrated population and a lot of farmland in one space. We have less than 3% of the watersheds having agricultural or developed land use. And our road density is still fairly low, same thing with population density, no concentrated animal feed operations, and our lakeshore disturbance score is about 11. So this scoring system is out of 35. You can have a max score of 5 across 7 different categories, so 11 is still in the lower third of that, and these disturbances look like things like industry and recreational uses of our lake shores in the valley. So some of the results of classification include, when considering all variables, including our ecoregion membership, as well as those physical lake and watershed variables, we see that the Northern Basin and Range and the Eastern Cascade ecoregion membership are the most significant. And so in these regions, we see a lot higher concentrations of total phosphorus. Now, when we consider all of these variables with total nitrogen, there was nothing that jumped out as significant. However, without ecoregion membership considered, so without that spatial constraint, we can see that the results change a bit. So for total phosphorus, precipitation emerges as being significant. Where there's more rain, there's actually less phosphorus in the water. In areas that have higher soil permeability in the watershed and deeper lakes, actually have less nitrogen associated with them. And so this was calculated using the ordinary least squares regression. Next, we input them into the correlation matrices and saw that none of them were highly correlated. This is good for us. This means we don't throw out any of our variables. And then next, we implemented the principal component analysis and the multivariate adaptive regression splines to pick out those variables that might be the most important for classification purposes. And so it was interesting to see that precipitation emerged, again for phosphorus, but also for nitrogen this time as being important, as well as water residence time for both nutrients. And then we saw lake surface area, so like that size of the lake actually was correlated with our phosphorus, and cation exchange capacity of the soil for nitrogen. So the reason I isolated these variables was because I wanted to see, out of a huge set of variables, which were the most important, right? For the subsequent regression tree analysis, I then ran 2 sets of runs for phosphorus and 2 for nitrogen, one being considering all variables and one considering just those that were considered important by the PCA and Mars analyses. So, and then that was repeated for total nitrogen. So the results differed for phosphorus and nitrogen, but they ended up being the same between both runs. And so precipitation ended up being the only important classifier once everything was considered. The total phosphorus split was at about 26 inches per year precipitation and nitrogen at 19 inches per year precipitation. And what I saw was that even though these numbers are different, that we have to remember that the population sizes of these are different, that the same lakes ended up on the same sides of both tree analyses. Once these classification variables were subjected to a K-means cluster analysis, I ran 10 iterations for total nitrogen and 10 for total phosphorus. I ended up seeing, using a cluster validation technique, that the similarity between these cluster iterations ended up being insignificant. The clusters did not stay similar enough to justify using that as a methodology. So here's what that tree looked like. We ended up having the Coast Range, Willamette Valley, Klamath Mountains, Cascades, and Blue Mountain Lakes on one side, and the Eastern Cascades and Northern Basin Range Lakes on the other. Now there are a couple of exceptions to this, primarily in the Eastern Cascades. So I wanted to visualize these statistics after considering our ecoregion membership. So maybe one of the ideas that's suspected of why we had some of those Eastern Cascades lakes fall into the other side of the classification tree is actually because they're, not only do they have more precipitation, but that it would be because their watersheds are primarily in the Cascades. So the second table here is all the Eastern Cascades lakes, and you can see here that these that were classified with some of their membership in the Cascades region ended up being in the Western Forested Mountains region, and the rest were on the other side. And so we saw some similarities too with this idea of correlations between where the watersheds are, these ecoregion memberships, and the nutrient concentrations up here with the Klamath Mountains. One was a traditional Klamath Mountain lake, and the other one ended up having majority ecoregion membership in the Cascades. And here in the Willamette Valley, we see that maybe there's not a statistical difference between the Willamette Valley lakes and the Cascades because the majority of their ecoregions are in the Cascades, or the majority of their watersheds, with the exception of Henry Hagg Lake, which is the only true traditional Willamette Valley lake considered in this analysis. So when we're visualizing this, here's one way to think about it. We have the log total phosphorus concentrations by ecoregion, and so the Western Forested Mountains represents that left side of the tree, and the Xeric West the right. And I was looking at this and saw that, yes, there's a statistical significant difference between our Western Forested Mountains and Xeric West, and this suggestive difference actually with this Eastern Cascades region in between. When I wanted to look at the within group variability for Western Forested Mountains, I said, oh boy, that's like a lot of ecoregions that ended up in one category. Upon closer analysis, here you can see that the Blue Mountains, Cascades, and Coast Range are not significantly different from each other. And here's our Klamath Mountains and our Willamette Valley, and we only had one lake for each of those, so it ended up not being feasible to make any conclusions about that, but we can see that these don't look like they're significantly different from each other. In terms of the log transform total nitrogen concentrations, we have, again, this Western Forested Mountain idea and the Xeric West. And here we can see, too, that there's a suggestive difference between these two categories, with the Western Forested Mountains having quite a few outliers. When I looked at those two regions across the Omernic ecoregions, I saw that these arrows pointing up are that Xeric West, and those pointing down are in that Western Forested Mountain category. And as you can see, those regions are significantly different from each other, so there's no real within group variability. There might be here in the Klamath, but we have one lake. I don't want to jump to any conclusions, so for right now, these are the only conclusions that we can make from this research. So what I found was sort of underwhelming as a criteria by rain shadow, perhaps. And here we have Mount Hood and the Columbia River. You can see Western Oregon on the left, central, and then over here this eastern region. And when we're thinking about the way that this broke up, this precipitation classification starts to make sense. So I wanted to remind you guys what the current suggested ecoregions look like. And you can see here we have right the Willamette Valley, the Western Forested Mountains, and the Xeric West. And I found that my classifications were not so different. We lose the Willamette Valley to the western forested mountains, as the majority of their watersheds are actually within the Cascades of Coast Range. And the Eastern Cascades emerges as kind of a transition category between the two areas. And then we have the xeric west remaining largely unchanged. For total nitrogen, we see the same thing with the Willamette Valley disappearing into the western forested mountains. And this time we have the Eastern Cascades becoming a part of the xeric west region. Now traditionally in that nutrient ecoregions that are proposed currently, we see that the Eastern Cascades are part of the western forested mountains. So this could be an interesting implication that the area is actually more similar to the xeric west. From these regions, I developed a proposed criteria. So this top table is the total phosphorus, and the bottom is total nitrogen. And you can see I included the median values for a good feel for comparison. So we have 5 micrograms per liter, 55.5, 340 micrograms per liter averages or medians for these 3 regions. And then for our total nitrogen, we had 245 and 540 micrograms per liter. So it's showing you some of the differences, especially with total phosphorus, those being like almost an order of magnitude difference. And so here's that 75th percentile we were considering for setting criteria. And you can see here that this variation is still pretty well represented with 11, 78.5, 490 micrograms per liter for these 3 different regions. And down here we have 277 and 760 micrograms per liter for nitrogen. And this 95th percentile is included as sort of a representative cap of what we would consider reference site nutrient concentrations and what we'd expect them to look like. So as you can see here, we have 32, 151, and 844 micrograms per liter across these regions for phosphorus, and 478 and 2,055 for micrograms per liter for our total nitrogen. And so we can see that there's quite a bit of variability between these categories, and maybe that these categories are pretty appropriate. When we hold these categories to that random sample of lakes from the National Lake Assessments talked about in the beginning, we can see some interesting results. We included lakes from these 2 different surveys across 2 different years. So in blue we have 2007, and purple we have 2012, with this particular graph being the western forested mountains total phosphorus criteria, and seeing how this random set of lakes perform. As you can see, the majority are actually, there's quite a bit of variability, but the majority in 2007 ended up being in this poor condition, and the majority in the 2012 data set being in this fair category. And how do we determine good, fair, poor? Good was anything under that 75th percentile that we're suggesting for management. Fair was between that 75th and 95th percentile, so in this case that's 11 to 32 micrograms per liter. And poor is anything that's not considered reference conditions. That's above that 32 micrograms per liter. When we're looking at the western forested mountain total nitrogen data, we can see that there's an inverse relationship with what we saw with total phosphorus. So we have the majority of lakes actually performing very well for the total nitrogen criteria developed for them. In the xeric west, we see a lot of variability between these years, and this could be due to the population and temporal variability in the times that these were taken. And we can see that in 2007 we have a pretty even distribution, with the majority being in poor condition, and then in 2012 we have 100% of the lakes meeting this criteria. For the xeric west total nitrogen criteria, we see that none of the lakes actually end up reaching that good qualifying condition under the 75th percentile, and that all of them are in this fair or poor category. Again, an inverse of what we just saw of that phosphorus. This is another representation of that disconnect between the phosphorus and nitrogen. You could be phosphorus, you can meet phosphorus criteria and not meet nitrogen, and be impaired in one but not the other. For the Eastern Cascades, the total phosphorus ended up being the 27% of it in poor, and 73% of the lakes in fair condition. Now there are a number of limitations with this research, as there is with all research, and so some of the things that I wanted to touch upon are things in the data set, so sampling, sample size, and the distribution. We collected this data across a number of organizations, and while we tried to standardize which samples were included, the epilimnion of summer surface values, there's going to be some inherent error where there's not a standardized procedure. Our sample size of 98 was not necessarily representative enough of all the regions and all the different natural nutrient conditions. And the distribution, we're missing 2 ecoregions altogether, the Columbia Plateau and the Snake River Plain didn't have any reference sites available. Omitted information and variables. When we're considering these nutrients, we were using weighted averages and percentages. Now we're losing a lot of information about that variability by not looking at the minimums and the maximums. We're just considering these averages and percentages. So there's information that could be useful that's being lost. And not every variable can be considered, right? So we considered a number of variables, but there's still some other drivers of the nutrient condition that might not be included here. Third is the inherent error. When we're trying to put the natural world on the computer, we're using GIS in this case, we could have some loss of this variability because of resolution. And I use 30-meter resolution with my delineating watersheds and calculating some of these raster variables. And in our vector data, there's still going to be some error in the boundaries of our layers. And additionally, each layer is created by a different person and a different organization. We have some inherent error that's going to come from that too. And when we have layers upon layers and we're calculating across different scales of layer, we're going to have some accumulation of error across this procedure. And lastly, I want to talk about the bias of percentile derived criteria. So this percentile, 75th percentile, is dependent on which samples are included and the sample size. So we could have 2 different samples across Oregon lakes and end up with different numbers because different lakes were included. And the same thing goes for sample size. 100 lakes might show you a different representation than 200 lakes. And additionally, there's this idea of this percentile derived criteria being a moving target. So depending on when we sample and when the analysis is done, could change that 75th percentile number. So there's a couple of conclusions we can draw from this research. And so there's ideas to take away from this thesis for nutrient management, and there's ideas of what we don't know and what need further research. So for some of these recommendations for nutrient management, these are mostly found by the thesis, but some of these are also literature substantiated. Is separate nitrogen and phosphorus criteria and classification. We're seeing that there might be different drivers across what is considered, or what would impact nitrogen criteria versus what would impact phosphorus. These reference conditions could be used for reference site determination for other lakes in Oregon. So those that weren't included in the data set could be could be compared across the reference condition set for their ecoregion that they're located in and determined if they're a reference condition or not. And this idea, especially of lake management by the watershed ecoregion, we're seeing that a lot of these lakes are sharing more, or their nutrient concentrations are potentially more impacted by the nutrients coming from the watershed that are outside of the watershed that they might be in if they're in too. So this idea, instead of managing by where the lake centroid is, managing where the majority of the watershed is located. Some of the more specifics, the Eastern Cascades being their own classification for phosphorus, and in the Xeric West for total nitrogen. In fact, there was a Pacific Northwest reservoir study that showed a similar result where the reservoirs of the Xeric West and the Eastern Cascades ended up being very, very similar and suggested to be managed together. Additionally, the Willamette Valley managed with the Western Forested Mountains would be another idea. We're seeing that again, this idea of ecoregion membership and where the watershed is could really be influencing the nutrient concentrations we're observing in these samples. Using the classification, though broad, it's a good baseline in refining criteria. So looking at this within group variability and studying just the Western Forested Mountains or Eastern Cascades or Xeric West in the future studies, and looking at that within group variability. And then we have this idea of soil permeability and lake depth being considered for total nitrogen classification criteria in the future. While it didn't didn't really rear its head much in this research, there's still that connection that this condition is, nutrient condition is linked to these properties. Some of these ideas for future research. The Columbia Plateau and Snake River Plain specifically need higher representation in terms of lakes. There aren't a lot of lakes in these areas, but the number of reference condition sites needs to be explored in this region and seeing what's practical. The criteria proposed might still be too restrictive, with some of those reference condition lakes not meeting that 75th percentile, as it excludes automatically that top 25%. And too broad in other regions. We might actually get some non-reference condition lakes sneaking in because we didn't consider all of the variables that could be impacting the nutrient conditions. So the additional literature actually suggests that grazing and logging would be very valuable to use in reference site choice in the future, and that there's a link between these things. And unexplained variability might be caused by other drivers of nutrient conditions. So there's two main ideas here. This idea of the variables that were considered, instead of considering them equally across the watershed, considering their proximity and their slope accessibility to the lakes. And so places that are watershed impacts that are closer to the lakes or at a steeper slope might actually have more of an impact than those on the other side of the watershed. Additionally, there's other variables we can always include, and so some of the larger natural nutrient drivers could be things like forest species composition for total nitrogen. And while I considered deciduous forests, this forest species composition idea might reveal specific species that are contributing more than others, such as alder, which is a nitrogen fixing organism, and geologic weathering in classification variables. So while ecoregion encompassed some of that geologic differences, it was at maybe too broad of a scale to encompass that local variability that phosphorus could be contributing to these lakes. Lastly, we want to consider some other statistical methodologies. So different statistical methods could actually improve the inclusion of reference sites in establishing criteria. So we don't have to exclude any in order to set this condition. And so one way is Jenks natural breaks optimization, which would set natural breaks between different levels of concentrations within the regions that are proposed. So, and with that, I will thank you again for your time and ask for questions.
What time is lunch?
Any general questions?
Would you recommend setting these criteria in certain seasons to look at the enforcement of those that would be more applicable, say, in the dry season or the wet season?
Yeah, so we use the standardization of summer as a time, right? We don't have as much accessibility to set the criteria in the wintertime, and as well as there's a better idea of some of that variability in the summer than in the winter seasons. There's different flow levels and things.
I have a question.
Yeah.
As a non-environmental scientist, can you remind maybe me about these different nutrient contents and what they actually mean? Like, whether they're good or bad, this phosphorus and nitrogen?
Yeah, and so the phosphorus and nitrogen are really good for biological productivity, which we would normally say is a good thing. But in the context of water quality, it's impairing our uses of water, right? So what recently in, I think it was like within the last year in Toledo, Ohio, right, their drinking water was compromised by an algal bloom. Dogs can get really sick from algal blooms. There's a number of other fish kills when there's really low dissolved oxygen caused by the dying off of these biological entities. It can be really bad for fisheries, causing these fish kills. So nutrients in some quantities are good, and there's natural nutrient variation in different kinds of lakes. We have like naturally eutrophic lakes and naturally alluviotrophic lakes that have different nutrient concentrations. And as lakes age, they gather nutrients, but what we're doing is speeding up that process quite a bit, and also changing these ecosystems so fast they can't keep up. Yeah?
I was curious about the Willamette Valley, and it looked like I don't know how many you started with of lakes in Willamette, but there was only one lake that was really included in this, like that met all your criteria for reference condition. Was there a wider?
Yeah.
Like how many did you start with versus coming down to that one that really met the reference condition?
So out of that 309, there were only 13 to start with, and 5 met reference condition. And then once we started to consider that ecoregion membership idea, it sorted out all of the other ones into the Cascades. And we saw that there's like some of that nutrient condition is more similar to Cascade lakes in this particular sample than the Willamette Valley, that one Henry Hagg lake. Yeah.
Okay. And were those all natural lakes, or were they?
Some of them were reservoirs. Lookout Lake was one of them. Lookout Point Lake was just I think a reservoir, and Henry Hagg.
Okay.
You good? Okay.
Well, I guess we can dismiss everybody else and get some snacks.
Yeah, so if you guys want, please help yourself food, all that good stuff.